So the next speaker is Zhang, and he's talking about modeling frequency response dynamics in power system scheduling. Ziyang, you may start sharing. Welcome. Ziyang received his degree in electrical engineering in 2019 from Tsinghua University in Beijing, China, where he's currently working towards his PhD degree. His research interests include renewable energy, power system operation, and power system planning. The stage is yours.
Could you hear me?
Yes, we can hear you well.
Thanks for your kind introduction. I'm sorry. Okay. Wait me. Hello everyone, I'm Zhang from Tsinghua University. My presentation today is to discuss how to model frequency response dynamics in power system scheduling. Let's see the background first. As we know, frequency security is critical to the secure operation of power system. As an important reflection of the active power balance between the loads and the generations, frequency should be maintained within a specific range in power system operation. Otherwise, the frequency violations may lead to the power outage, such as the London blackout on August 9, 2019. I'm sorry. Okay. One reason of this accident is the high share of renewable energy before the contingency. In fact, the high penetration of renewable integration has significantly challenged the frequency security of power system. First, the uncertainty of the renewable energy increased the risk of the occurrence of power imbalance. Second, renewable energy would decrease the system inertia. A low inertial system may face faster frequency drop after contingency, and the frequency reserves also become scarcer because most of the renewable generations don't participate in the frequency control. Thus, it is necessary to consider frequency response dynamics in power system scheduling. However, it is maybe not very easy because frequency dynamics are captured by differential equation or transfer function model with nonlinear terms, such as the swaying equation or the multi-machine system frequency response model, for short, MMSFR model. And there are several factors influencing the frequency dynamics, such as the system inertia, load damping factor, frequency reserves, and the governor characteristics. But power system scheduling is generally modeled as linear programming or mixed integer linear programming. Thus, frequency security should be formulated as a linear algebraic constraints. But when we transform the differential equation or the transfer function model to the linear constraints, simplifications and approximations on frequency dynamics are necessary. This may raise two questions. The first one is how to quantify the accuracy of different frequency security constraints. And the second one is how to consider more details of frequency dynamics in frequency security constraints. For the first question, we propose the evaluation method, and for the second question, we formulate a lower frequency security constraints, namely frequency security margin model. And this slide gives the framework code of the evaluation method. It consists of 4 paths. In the first path, we use the operational simulation to cover sufficient possible operational statuses and take them as data set. And in the second part, we simulate frequency dynamics after contingency of each operational status and take the simulation results as the benchmark of frequency dynamics. And in the third part, we judge whether frequency security constraints are satisfied in at each operational status. In this part, we compare 3 different frequency security constraints. Apart from our proposed FSM model, we also choose 2 typical frequency security constraints, namely LFSM model and IDFR model. These 2 models are proposed in the following 2 papers. And in the last part, we compare the results of the model test and the benchmark of the frequency dynamics, and 4 indices are applied to evaluate the performance of these frequency security constraints. And the 3 different frequency security constraints and the 4 evaluation indices will be introduced in the later slides. Let's say the LFSA model first. This model makes two simplifications based on the swaying quotient. It both neglects the low damping and simplifies the gathering characteristics. It assumes that the generators adjust their output with a fixed ramp rate, like this figure shows. And after these two simplifications, the swaying quotient will be simplified like this. And from this simplified swaying quotient, we can obtain the approximated frequency layer and calculate the upper bound of the time when frequency layer occurs. Thus, these two constraints limit the maximum frequency reserve provided by the generator before frequency layer. And to ensure the frequency security, the frequency reserve should be larger than the power imbalance. As we can see in this model, all these constraints are linear. Thus, we call this security constraint model. And for short, we name it LFSA model. And different from the LFSA model, idea of our model considers the load damping factor, but only simplifies the gathering characteristic. It assumes that the frequency reserve is delivered within a certain time. And from the simplified swaying quotient, we can calculate the frequency layer. And we can prove that the frequency layer monotonically increases with the multiple of the system inertia and the frequency reserves. Such that to ensure the frequency security, this multiple should be larger than its bound value, K superscript star, which is the solution to this equation when frequency layer equals to the allowable minimum frequency. And as we can see in this model, the frequency reserve requirement is related to the system inertia. That's why we call this model inertia-dependent frequency reserve model, for short, IDFR model. Unlike the above two models, our proposed FS model both consider detailed gathering characteristics and the low damping factor. Inspired by this paper, we aggregated governance in MMSF model and obtained aggregated system frequency response model, for short, ASF model. According to the ASF model, we can obtain the analytical frequency layer. And furthermore, we can calculate the maximum tolerable power imbalance. And in this presentation, we named it frequency security margin and use the pipelines to approximate the nonlinear term in frequency security margin. We can formulate the frequency security requirements based on the frequency security margin. That is, frequency security margin should be larger than the power imbalance. And this slide gives the overall frequency security margin model. Apart from the frequency security requirements obtained in the last slide, there are other constraints. These three constraints indicate that frequency response factors can be linearly expressed by the operational statuses. That means these constraints link the power system operation and the frequency security. So you can change the operational power system operation to maintain the system frequency security. And these constraints indicates that the generators participating in frequency control should have sufficient reserve space. And the nonlinear term in this control, in this constraint can be linearized by the big M method. So far, we have introduced the three different frequency security constraints, and this slide gives a brief comparison of these three models. As we can see, our proposed FS model consider more details of frequency dynamics. It both consider low damping and the gathering characteristics. However, it also introduced the more decision variables and constraints in power system scheduling model. Thus, we can see when more details are considered in frequency security constraints, the model also make a compromise on the computational complexity. We have introduced the three different frequency security constraints, but how can we quantify their accuracy? From the operational simulation, we can get a series of operational statuses, but frequency security constraints can be regarded as a binary classifier of the operational statuses. For each operational status, the classification results belong to one of the four groups. Thus, evaluation indices of the binary classifiers can be used to quantify the Franken security constraints. And in this case, these indices also have more physical meanings. When the Franken security constraints make more right evaluations, the accuracy score would be increased. That means accuracy score reflects the recognition rate of the Franken security constraints. And when more insecure operational statuses are wrongly evaluated as secure, that means the system is more conservative. This may lead to the increase of the operational cost in power system scheduling. So recall score means the conservatism of the power of the Franken security constraints. And when more security statuses are wrongly evaluated as insecure, this may lead to the insecure of the power system operation. That means the precision score reflects the reliability of the Franken security constraints. And the F1 score is the harmonic average of the precision and the recall. That means F1 score reflects the comprehensive performance of the Franken security constraints in terms of the in conservatism and reliability. So let's say the case study, we conduct our case study based on modified HVRTS 79 system. The penetration of renewable energy generation is about 29%. We use the GOPT developed by Tsinghua University to simulate the operational statuses over a whole year. In total, 8,716 points. And the left figure shows the operational simulation results over a week, and the right figure shows the distribution of the system operational statuses. And let's see the results. The upper table shows that our model performs best among the three models in terms of accuracy, precision, and F1 score. And the left figure shows the evaluation results of the different models. As we can see, the boundary between the secure operational statuses and the insecure operational statuses is generally decreased along with the increase of the system inertia. That indicates that the non-inertial system may have a higher requirements on frequency reserve. This is the same with what we have introduced in the background. And the red figure compare the evaluation results of the three different models with the benchmark. As we can see in our proposed FSM model, there are very few insecure operational statuses are wrongly evaluated as secure. That means our proposed FSM model is the most reliable frequency model among the three security constraints. And this slide gives us sensitivity analysis of the model performance on the penetration of renewable energy. The left figure shows the distribution of system operational statuses on the different renewable energy penetration levels. As we can see, operational statuses on the higher renewable penetration levels are more dispersed. And there are more operational statuses is in the left lower corner of this figure. That means the system under higher renewable penetration are more likely to be operated in the low frequency reserve and low inertia condition. This may lead to a frequency security problem. And the red figure shows the evaluation indices under different renewable energy penetration of the three different frequency constraints. As we can see, our model always performs better in terms of accuracy, precision, and the F1 score. And the accuracy of our proposed FSM model is remain the same and above the 95% because more details are considered in our model. This shows the robustness of our proposed FSM model. Let's summarize my presentation. We propose an evaluation method to quantify the accuracy of frequency security constraints. And a lower frequency security constraints FSM model formulated to consider more details of frequency response dynamics. The proposed evaluation method shows that our proposed FSM model have higher accuracy than two typical models. And our future works will be focused on formulating frequency security constraints to make a better choice between accuracy and complexity. So that's all. Thanks for your listening.
Thank you very much for your presentation. We have a few minutes to answer the questions. There's actually a raised hand, Sebastian. I will allow you to talk if this is a raised hand about this talk.
I have seen some question in the Zoom, and the first question is, what is the difference between IDFR model and LFSA model, both a Schumann constant ramp rate? Right. In this model, they both simplify the governing characteristic as a ramp rate, but the IDFR model further assumes that the all frequency reserve is delivered within a certain time. That means they include the ramp rate between different generators, but LFSA model consider this difference. So I think this is the difference between these two models. The same all over.
The second question, it's similar to the fourth one probably. You assume a single synchronous area with the frequency being the same all over the network. Is the assumption valid, and under which conditions?
I think this assumption is not valid under any condition, because when you use the DC lines to connect the two areas, this may have different frequency among these two areas. So I think this assumption is only maybe more applicable to the AC grid.
Maybe we have time for another question. Minhui.
Okay.
You use equivalent inertia H and system damping coefficient D for the 70 bus grid. How do you estimate these values?
In this case, I set the inertia of the generators according to their common range is about 4 seconds to 8 seconds, and low damping factor D is set to be 1%. And I ask the next question.
Sure.
Under which condition is the single machine representation of a multi-machine power system applicable? This assumption is proposed in this paper, and in this paper, this approximation have some there are several approximation error in this simplification. Is about 5% in this paper, but I have not conduct the error analysis in my presentation, so I can't answer this question now.
I think we will have to take the rest of the questions offline, unfortunately. Otherwise, we won't have time for the next speakers. But thank you again, Ziyang, for the interesting presentation and motivating presentation.
Thank you.